I think you do have most of the theoretical things you need to know about neural networks, and then from now on is basically adding up like more operations, more state-of-the-art solutions which you can use with neural networks. So convolutional neural networks were somehow going on in parallel with the classic multi-layer perceptron. There are still feed-forward neural networks. There is no recursion happening there. But many people just got interested in these networks because of the problem of computer vision. So computer vision was one of the key problems in artificial intelligence in general, because they want to have a machine which is looking like a human or behaving like a human. It just looks at one picture, one specific scene, and can just infer from that something, right? And then one of the basic things was to just recognize patterns, right? Pattern recognition was one of the basic tasks. And basically what you do with MNIST is, again, a sort of pattern recognition, because it's going to recognize the pattern of the number, right? So it's 3, it's 2. So that classification is, again, sort of pattern recognition. But you can do it in more general case. So the idea, similar to multi-layer perceptron, the idea was, again, motivated by biological studies. So quite well-known study by Hubble and Wiesel, who won like 30 years after they won the Nobel Prize. The idea, like, it was a kind of very, say, one of those things in science which is hard to grasp or digest. So they really opened up the cortex of cats and put the electrode there to see what's going to happen when the cats are seeing a scene. And then they started to just understand how the visual system or visual cortex of a live creature is reacting to visual scenes. So this was the point where they started to somehow develop a computational model pretty much similar to what people did with neuron, the basic neuron. And then Fukushima got this idea, their modeling, and then he just proposed this new cognitron. So it's like a perceptron, is now visual version of that. And the idea was that he wanted to just computationally mimic what was going on in the visual neurons or visual cortex of a live creature. And then he actually proposed this one in 1979, and then at that point, people just saw the idea. It sounds, it just seemed to be working, but the problem was computation, right? Of course, we did not have enough computation power to do the backpropagation, right? And then one of the first people who started to just do serious backpropagation on these architectures, which later on became like known as convolutional neural networks, was Yann LeCun. And you probably know Yann LeCun, right? So he's one of the famous people in like, alongside with Geoffrey Hinton, they're a couple of people who are very well known for computational machine learning, and he's one of the ones, right? And he is still very active. So he just proposed the LeNet, right? And this was a network which was a very simple convolutional neural network. He wrote down the backpropagation for that one, so he could efficiently backpropagate over that and train it. And he trained it to just recognize a bunch of letters, right? So it was not MNIST numbers, letters. And then it was one of the first networks which worked. But again, people at that point of time were not very happy, because they didn't think that this is going to just expand or extend in dimensionality very fast. Up to 2012, where here at UofT, people just developed AlexNet, and it worked, right? And this was the point where everything started to boost up. So what we are going to talk about is convolutional neural network. They are CNN, not the CNN news agency, but we're just referring to them as CNN. And what we want to know, few things. First of all, we want to know what is the key difference between them to the classical multi-layer perceptron. they are, like a bit of a spoil right now, they are multi-layer perceptrons, giant ones, with not fully connected layers, just locally connected layers with shared parameters. But you're going to see that why this is happening and why that is efficient. So we're going to just learn that, and then we'll learn how, for example, we can go forward, how we can go backward, and that one is quite intuitive. And since everything is dual, this is a very efficient architecture that you can use for visual tasks usually. So CNN just is a fully feed-forward neural network, because once the information goes in, every layer is going to process the features of the previous layer, right? So there is no recursion happening here. So this is a feed-forward neural network. It has standard fully connected layers at the very end, that's right, but it has also some extra layers, convolutional layers, pooling layers, and these are things that we want to just learn. So basically, we first want to find out what is convolutional layer, what is pooling layer, and how does it do the feature extraction. How does it look at a scene and starts to just build a bunch of features in the next layers. So let's start with one example. So a very simple example, which is going to motivate you why we are happy with convolutional neural networks. Say I want to classify MNIST data set. So that is a simple task we have done in the previous chapters. And there is one key difference here, and the difference is that the image that I want to look at is not like a standard 28 by 28 MNIST image, right? It's a larger image, a larger white background, and then the image is somehow located, say, at top left, right? So I have this large background, and the image is somehow put here, right? The handwritten digit is written somewhere on the top left of that image. And I want to just train some neural network. If we want to use what we know up to this point, what can we do? We obviously want to use the MLP, right? So say, for instance, this background is 3 times larger than the actual MNIST. So instead of 28 by 28 is 3 times 28 by 3 times 28, right? 84 by 84, right? And your MNIST image is top left in this input, right? Now, if you have this one and you want MLP, what is the number of inputs that your MLP has? It's going to be that number, right? 84 times 84 is 7,056, right? 7,000 different inputs you're going to have, right? The normal MNIST has 784, right? And this is roughly 10 times, actually 9 times more than that, right? So you're going to have 9 times larger input, right? Well, is the task different from the normal MNIST classification? Doesn't seem to, right? So if I do know that here is the top left image, and I do know how to classify MNIST, I should be able to classify this one as well, right? If I cut this image properly into 28 by 28 and give it to the neural network, which is able to classify MNIST, I can classify this one as well, right? The only issue is that I should find out the place and cut it, right? So that is the new trouble. So, but say I don't want to do that. I want to have everything like fully automated. So I'm going to give this 7,000 inputs into a multi-layer perceptor, and I train that one, right? Now, if I want to train this, I need the corresponding data, right? So I'm going to go inside MNIST, and I get the MNIST images. I put them all in this big background. I put them on top left, right? And I make new data set, right? Every single sample inside this data set is MNIST sample, which is located at top left, and then I have extra background, right? Everybody's cool, right? So I make this data set, and now I train on this data set, right? Now, say I do the training is over. Now, if I give such an image inside to this neural network, this is going to recognize it as 3, right? It's going to classify it as 3. But what if I give this one to this neural network? What do you think? Do you think that that neural network that I trained is going to classify this guy as 3 as well? No. What is the reason? Right, exactly. So when you are training, it gradually is going to understand that these guys are simply background, right? So their corresponding weights should be roughly 0, right? You don't really need them. You only need to focus on this one, right? So this is the way the neural network starts to learn, right? I need to focus on top left, right? And inside that, I need to extract features, and out of that, I find out what is the digit, right? This is the way the neural network gets trained, yes? Right. Yeah, but because when I made my data set, I only put samples here, right? So I'm going to talk about that later. So no worries about that. So yeah, I mean, if I do right augmentation, that's going to fix it, right? But right now, if I don't do any augmentation, this is not going to classify this one as 3, right? So it can classify any image which is at top left, but it's not going to classify this one properly. Everybody's clear? Right? So this is not going to be classified properly if you just do the process I told you, right? But now, what you can do, well, I think, so the main reason that it's not classifying properly, as I said, because neural network learns to just look at the top left and then classify the image. This is not the case. Now, what can we do? Basically, your friend said, we can do data augmentation, right? What does it mean? It means that I can get my one, or any sample that I have, I don't put it on top left, right? I make one sample top left, another sample a bit right, another sample more right, another sample MNIST is in the center. So I get one sample, one MNIST sample, I put it everywhere possible, and I add all of them as samples into my data set, right? So I say I don't need to put 3 here, so 3 here, 3 here, 3 here, everywhere, right? And all of them are now samples for my training, right? And now I train on this data set, and this one, well, it's going to work, right? But there is one question. I have, like, if I have one sample, one MNIST sample, how many of these augmented samples I'm going to make? Well, not only 8. I mean, I can do much more, right? I don't really need to just put this guy here, right? I can just slightly put it right? Yeah? Yeah, 1 pixel by 1 pixel. I can go ahead and do all of it, right? So this is not a simple thing, right? So it's going to be a huge number of samples. I mean, of course I can make it. I can train the neural network on that data set. But the question is it so complicated task that I need so much of computation? Because this is going to be a huge data set, a huge training loop, right? Do I need that? Well, no, because I do know that if I have a neural network which is able to recognize 3, then that neural network, as long as I tell it just look at this point, it's going to recognize it, right? So it shouldn't be a very complicated task. And this is basically how we work as intelligent creators. Because when we look at one scene, we don't, you don't really need to see your kid inside a huge population only when you have seen the kid there, right? So you can simply recognize, oh, my kid, right? Because your brain somehow starts to get used to your kid, right? And then you are going, like, it's going to give you large signals when it's just seeing that particular part of the scene, right? So you ignore everywhere else inside the scene. You just focus on that part, right? So this is exactly what's happening in human brain. And this was the output of the study by Hubble and Wiesel. And people based on that came up with a better idea. So we don't really need to give the whole field, whole scene as an entire input. Typically what we do as intelligent entities, we usually break visual fields into parts, and then we try to grasp information from every single part, and then through iterating or through multi-layers of this process, we start to get focused on one particular scene, part of the scene, right? So this is how our brain works, and so it searches within smaller fields, which we usually call it receptive fields. So it's going to look into some smaller parts of the field, and then gradually it's going to just start getting sense about that scene, right? So same thing is going to we want to mimic the same thing inside the neural network. So how can we do it? Let's first start trying it for this same example. Okay? Say I have this neural network, and this neural network has been trained on MNIST data set. It means that you're going to get 784 samples, right? Input, 784 pixels. And out of that, you're going to tell me what is the class. It's 0, 1, 2, till 9, right? It's going to tell me what is the digit. I'm going to do one extra modification to that. So I'm going to add one class, which is class empty. It means that if I give a complete empty image to it, it's going to tell me it's empty. Okay? So it's just one extra class, right? It's not going to be any problem. And this is actually no training going on, right? Because for completely like nonsense input, it's going to just give me empty, right? Okay? So let's say that I have done this, and now I want to use that neural network to somehow find out what is the number written inside my larger background, right? What can I do? I can get my neural network, and I can break it into parse 28 by 28 fields, right? And I get my neural network, I give my neural network first the first part, then the next part, and so on, right? So when my neural network looks at this first part, what does it say? It says that this is class 3, right? Because say my neural network has been trained well, right? So it's going to look at this one, and it has been trained well, so it can recognize it as 3, right? Then I go for the next field, right? For that field, it's going to say empty, right? Empty, 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 and so on. It goes till end, right? So it's going to tell me, well, you just gave me lots of fields, lots of parts. The first one was 3. Rest of them were empty, right? So you have 1 3 inside this image, right? And there is a 3 inside this image. If I give it a complete blank, then it's going to go over it and tell me, well, it's blank, right? So this is basically the test that I wanted to do, right? So what I can do, I can get this guy, and then every time I go over one particular part of it, which is 28 by 28, and then at the output of the neural network, if I see one digit, so if it says 3, I'm going to keep it. If I get something which is like the empty case, I'm going to return false, right? And if I always get false, then it simply means that there is nothing inside my image. If I get at least one non-false, one true, then it means that I have one digit inside this image, right? So what I can do, I can just collect the output of all these parts, and then I OR all of them, right? If I OR all of them, if I have just a single non-false, non-empty case, non-empty part, then I'm going to recognize it as a digit, something inside this image, and that is this particular digit, right? Everybody's clear? Yes? Yeah, we are not going to do this like this. We are going to just make it more concrete, yeah? Just to give you the idea. Like in the next example, you're going to see that. Yeah. Yes, because my neural network can take 28 by 28 as input, right? No, we're gonna build a general case. Actually, 28 by 28 is too large. You can do it with a smaller one. Yeah, but we're gonna talk about that. No worries. But you got the idea, right? So the main idea is that I don't need to get my whole image as a complete scene. What I can do, I can break it down into parts, and then I just scan those parts, right? And out of this scanning, if I get anything, then I'm gonna recognize it as that thing, right? So this whole idea, what we do here is basically convolution. So convolution is nothing by doing a linear computation plus scanning, right? So you have same weights going on the same image, scanning it, right? And by scanning it, you're extracting new bunch of informations, right? So the information we collected here are that like this, like 3, empty, empty, and so on, right? And you keep on going, right? So these are new features that you collect out of this image, right? Now, That is the simplest form of CNN. So basically what CNN does, or what convolutional layer does, is that you're going to have a linear layer, and that one is going to scan the input map, right? And no worries, I'm going to explain how exactly it works. What is map? We're going to get used to these expressions. And then this scanning procedure is usually what we call it convolution. If you think about the convolution you know from signals and systems, this is the two-dimensional version of that. Like there you do is usually one-dimensional because you get your filter, your whatever impulse response is, and then you just, well, you first reverse it, that's not important, but then you put it somewhere on the input signal and you start to scroll it, right? And each time you just compute the average. That is again convolution on one-dimensional signal. This is convolution on two-dimensional signal. You can do it in higher dimensions as well. And what we can see, you don't see it right now immediately, but we're going to see it like like after the next section. You're going to see that this CNN is again a giant feed-forward neural network, a giant multi-layer perceptron. The only difference is that every single input or every single neuron is not connected to everybody in the next layer. They are connected to some, they are not connected to some others, right? For example, here, like if you think about this first pixel here, right? This first pixel is connected to the first copy of this network, but to the next copies it's never showing up, right? But we're going to talk about that. We're going to see that clearly, okay? So basically, convolutional neural networks are a kind of wise way of forming your MLP, those connections in MLP, where you don't need a huge number of connections. You just have significantly less connections. They have one other key feature, which is that they have shared parameters. But as I said, we're going to see that later on, okay? Now, let me just start with one example. We just finished this example, and after that, like on Friday, we're going to talk about different components of convolutional neural networks. So let's get into this one, which we had in assignment 1. So in assignment 1, you had this 3x3 image, right? If it is pattern X, then you're going to recognize it as 1, right? Your neuron. If you have any other thing, it's going to recognize it as 0, right? Right? So that was the classification that you did in assignment 1. This was a perceptron. Here you have a step function, right? And then how many weights do you have here? 9 different weights, right? The bias is 0. Okay? Set the bias to be 0. Okay, I put the bias here, but you can put even the bias 0. No, not important, right? Now, I have these 9 different weights. What is happening when I am, for example, passing this guy through this perceptron? Well, the first guy is getting multiplied with W1, right? The second pixel gets multiplied with W2, and so on. The last pixel gets multiplied with W9, right? You add them up. What comes out of it that it classifies the image as 1? The number that comes out of this, is it positive or negative? Positive. It's definitely positive. It's positive, it's going to get classified as 1. Any other image I give to this perceptron, after doing that calculation, what is the sign of that number before activation? Negative, right? Because any other pattern going inside this perceptron is classified as 0, right? So any guy coming here is going to be negative and then classified as 0. Only pattern X, when goes inside this, it's going to be positive and then classified as 1, right? So we did it in assignment 1. That was quite easy. Now what I want to do, I want to use the same perceptron that you trained there. I want to use that to just recognize one pattern X inside a larger image. So something like this, for example. Say I have a 10 by 10 image, and then there is 3 by 3 X inside that image. I want to see whether this guy is there or not, right? So what I do, I'm going to use a 3 by 3 filter. So what is filter? Is basically those weights that we have, right? So this means that this guy is 10 by 10. You see here in between I have a pattern X, right? Now I want to give it into the same perceptron we had before to use it, this guy, to recognize whether there is pattern X inside this image or not. What I do, I'm going to put one filter. You see this red filter here, right? It's 3 by 3, right? The first entry inside the filter is corresponding to the first weight here, right? The second entry is corresponding to the second weight till the last one, right? What I do, I'm going to put that filter on that part of the image. I multiply every weight with the corresponding pixel on the image. I get the output computation. I pass it through that perceptron, right? That activation, right? And I write down the corresponding number here inside this one, right? You see this, what I'm doing? So this guy, this first part, goes inside this perceptron. What comes out of it? 0. Why it's 0? That guy is not X, right? That guy is not pattern X. Everybody's cool, right? What's going to happen if I shift it a bit right, 1 pixel right? It's still 0, right? It's not going to change, right? If I go again right, what's going to happen? Again 0. If I keep on going towards very end, it's still 0. Now I finish with the first row of scan. I want to get into the second row, right? What I did, I just pushed my filter 1 by 1, right? 1 pixel by 1 pixel. Now that I want to come down, I again come down with 1 pixel, right? And I start again the same point, right? So this means that I get that guy. I bring it up here. You see it, right? So from here, I just bring it up here. I just came 1 row down, right? Clear? OK. Now here, again, this guy goes inside this neuron. This is going to give me 0, right? Because this is not pattern X. What's going to happen if I just push it 1 step forward? 1, right? Because this guy is no 1, right? This is pattern X. And I keep on going again, I'm going to get 0. Now, what is going to happen is that when I just get that filter and scan all of this image in the way that I did, then I'm going to have one map here, right? I have a map. Every single number inside this map is corresponding to one part of that image, right? So for example, this 0 corresponds to the output of this part of the image, right? The classification I have done on this part of the image, right? Now, I look at this guy. Is there a pattern X inside this one or not? Yes, because there is 1 here, right? There is at least one entry 1 there, right? And because of that, I would say, OK, there is 1 X there, right? If I had more, then, yeah, definitely I have multiple of them, right? Everybody's clear, right? So this guy is just extracting a map of information about this one, right? And this process that I am doing, this one, is convolution, right? I do it via 3 by 3 filter. That filter is the same for every single computation that I do, right? I didn't change the weight from this part to this part. All the 9 weights are kept fixed, right? So I have fixed weights. I put them in the form of a filter, and now I start to scan the image, right? And when I scan the image, each time I compute one number, I put them here, I'm going to end up with this map of features, right? And out of that map of features, I can now argue whether there is a pattern X or not there, right? Everybody's clear, right? So this guy is enough to just recognize X because there is only a single 1 here. And what I could do, basically, for example, I could say, OK, I compute the summation of every entry here, right? If it is more than 0, then obviously there is an X there, right? Or I just do OR, right? Logical OR on all of them. If it's 1, then it means that there is an X here, right? Now, one thing that you might recognize here is that you don't really need to save the value 0 or 1 values here. You could do it without activation as well, right? How can I do it? Let's look at this image again. Say that I give it to the same perceptron, but I do not activate, right? So I remove the activation. This means that the value I get out of the perceptron here is one real number, right? So it's going to then pass through the step function to get 0 or 1, right? Now, what's going to happen if I send the first part through this neuron? the number that comes out, what is the sign of that number? Negative. Because this is not pattern X. This is supposed to be classified as 0. This means that before activation, I had a negative number, right? What about the next part? What if I go one pixel right? It's again negative, right? This guy is negative, this guy is negative. I keep on going, this one is negative. Now, what if I just go one step forward? That one is going to be positive. Anybody else is again going to be negative, right? So if I build this map of features by doing this scanning without activation, I'm going to have, again, one map of lots of numbers. All of them are negative. One of them is positive, right? And that positive one is actually corresponding to my X pattern, right? So basically, I don't need to really activate every single one. I can just compute this whole map. And once I am over, I'm going to take the maximum value of that, and I activate that one, right? If the maximum value is positive, then this means that there is definitely one pattern X, and then I classify it as 1, right? If the maximum value is negative, this means that there is no pattern X here, and then the classification is going to be 0, concluding there is no X inside this image. Yes? Yeah, if you are, but maybe, for example, you want to know how many of them you're seeing, right? So, yeah, it's just an example. But if you only care about one pattern X, right, you can stop at that point, definitely. Yeah. So, moral of the story, you don't even need to activate for every single computation, right? You can just do the activation at the very, very end, right? Now, this guy that you compute, as I told you, this is what we call it feature map, right? And feature map are a bunch of numbers. Those numbers are giving you some feeling about the scene you have shown to your neural network, right? And this guy is the input map, right? And map simply means two-dimensional array, right? A matrix of numbers, right? So you have one input matrix, one map. This is going through this process, and it gives you a new feature map. And that feature map, based on the numbers inside that, you can conclude whether there is pattern X or not, right? So that is the input image or input map. This is the feature map. And this guy, which you use to just go over your image, this is what we call it filter, right? So this is the filter. It just has a bunch of weights, goes over a part of image, do the computation, goes over the next part, and so on till it's over with the whole image. Everybody's clear? So now, the process of computing that output feature using this filter from this image, this is what we call it convolution, right? So what we are doing, we're getting our image, and we are convolving it with the filter with the stride 1. I did the stride 1 here, okay? So can I do it with larger stride? Sure. What's going to be if I do it with larger stride? So by stride 1, it simply means that every time that I'm over with the computation, now when I want to just push my filter, I just push it with step 1, right? So if I want to take it right, then I just take it 1 pixel right, right? Again, 1 pixel right, and so on, I finish, right? So this is a stride 1. And again, when I finish there, I go 1 step down, and then I start from left again, I keep on going, right? So this is the convolution process with a stride 1, and I do it with the same filter for every part, and then at the output I'm getting a bunch of numbers. That is the feature map coming out of the convolution process, right? But I can do it also with the stride 2. If I want to do it with the stride 2, what should I do? I don't jump with 1 pixel. I jump with 2 pixels, right? So the thing, this is here. Now instead of like W1 is not going to be only 1 pixel right? So it's going to be 2 pixels. So I'm going to jump. You see it, right? So from here, I'm jumping with a step 2 now, right? Again, when I'm finished with this computation, I'm going to jump again with a step 2, right? Again with step 2 till I am finished, right? If I now want to just jump further, right, with a step 2, I get out of my input image, right? You see it, right? If I want to jump with a step 2, then W1 should now be on the place of W3, right? And then the last column is getting out of the input, right? So I don't want to do that. So I'm going to just jump down, right? And when I jump down, I again skip 2 lines, right? You see it, right? I skip here, and I keep on going. Now, this is again the feature map that I compute with the stride 2. And one thing that you see, when I just increase the stride, the output feature map is getting smaller. Makes sense, right? So roughly speaking, if you double the this stride, you are going to shrink your feature map with a factor 2, right? So that is convolution with a stride 2, and then you can actually define convolution in general. So this is where we are going to start next time, but you can take a look at this expression. Just try to look at this expression to get a bit of sensing, but no worries, I'm going to explain it. So it's not a big deal. This W is basically that red filter. Is going to get multiplied with the ij part of your image, so you just look at one part of your image. Once you multiply them, you sum them up. This is the corresponding entry of your feature map, right? Exactly the same procedure we did in that example. You can, in general, do it on any image, and that is what we call a convolution, okay? Questions? No questions?